Hello everyone, thank you very much for the chance. In here, I would like to present a part of our research entitled A Neural Primitive Model with a Sensorimotor Coordination for Dynamic Quadruped Locomotion with Malfunction Compensations. This is our research collaboration between Tokyo Metropolitan University and also EPFL. Locomotive capacity is essential for movement in a dynamic environmental condition. Animals exemplify this, having to move efficiently to conduct their activities. Quadruped animals, specifically, produce a dynamic locomotion pattern ranging from walking to galloping. These patterns are generated by CPG structure using sensory feedback and spinal reflex. Primitive CPG structures generate a dynamic pattern even when sensory feedback and signal commanding are absent. In the past last 2 decades, integrating neuroscience and robotic locomotion has been considered as an alternative approach to dynamic locomotion. Many researchers have proposed CPG concept in a service of robot locomotion. However, the question of the best way of controlling quadruped locomotion has yet to be resolved. Quadruped locomotion based on CPG is a part of various strategy for controlling speed and direction. Some researchers have used mapping selection of the CPG network to generate various gate patterns. However, generating different gate patterns without appropriately reconstructing the network is still challenging, which is creating an efficient structure that can generate dynamic pattern and develop integration of sensory feedback to establish swing timing have still not been achieved. In some cases, the spinal cord system of human and animal regulates locomotion when a leg is injured, changing the role of sensory feedback within the locomotion network. Considering the sensory motor coordination mechanism is important for developing dynamic locomotion in case of malfunction. This paper responds to the current challenge facing developing CBG for quadruped locomotion, presenting an efficient, robust CBG model that is dynamically integrated with sensory feedback to generate various gates while also considering leg malfunction compensating without involving too many parameters. The proposed model has novel contributions as follows. First, developing a robust CBG model with an efficient structure that can generate various gate patterns. Second, integrating sensory feedback that substantially impact the CPG modulation output. And the third, considering dynamic sensory integration to compensate leg injuries at the various speed. To realize the objective, we developed two-layered CPG model incorporating rhythm generator RG and pattern formation PF, where one RG represents one leg's movement pattern and one PF neurons represent the activation of one muscle. Since each leg uses 4 muscles, there is one RG neurons and 4 PF neurons for each leg structure. Rhythm generator neurons generate oscillation signals responsible for controlling the pattern of a certain leg. All of RG are interconnected and control the timing of the leg swing action. Sensory feedback is critical for adjusting CPG modulation. Proprioceptive signals from the leg force and swing pace are integrated with the rhythm generator neurons in the CPG. Leg malfunction affect the integration of sensory feedback and RG. A neuron representing a certain injured leg sends a signal and influences the effect of the sensory signal on the RG structure. We use neural oscillator of Matsuoka model as an inner state of RG neurons calculated in equation 1. The received inhibition effect of its self-adaptation Vi and the signal from other RG neurons Yg influenced by kinetic weight WRGIg. Vi calculated in equation 2 and Yi calculated in equation 3. The inner state and self-adaptation effects are respectively influenced by time constant tau and t. The RG neurons is also influenced by sensory feedback alpha I from ground force afferents, swing-related afferents, and nociceptron or Ni. In equation 4, alpha I 0 is the basic stimulation of the I neurons. WFRIJ is the kinematic weight of the force afferents Fi, and WSRIJ is the swing pace afferents Si of the E leg to the G RG neurons. W and S is the weight representing the influence of the nociceptor neurons. RG neurons transmit the firing signal PI to all PF neurons in a certain leg to activate swing behavior. The value of each reference is calculated in equation 6. The PF neurons control the timing of each muscle contraction calculated in equation 7, where PFI calculated in this equation 8, and also the value of micro calculated in equation 9, and W is calculated in equation 10. Then after that, the signal to the muscle stimulation can be generated through the PF neurons. To find the best CPG structure, we optimize the weight representing the interconnection of RG neurons WRG and those representing interconnection with sensory feedback WFR, WSR, and also WNS using a single objective evolutionary algorithm. There are two optimization steps. First, building a dynamic gate pattern, and the second is building the malfunction compensator. This optimization aims to identify the best interconnection of RG neurons and integration with sensory feedback for generating dynamic gate pattern without changing the interconnection structure. Those parameters are represented by 23 parameters Ri until R23, optimized using a single objective evolution algorithm where we can see the value of Ri until R23 is tabulated in the table. We minimize the error of speed oscillation, desired speed, and also the speed stimulation. For each evolution process, we perform the robot simulation 6 times at different speed stimulation compared to the parameter tau f in equation 1. Each performance required 1000 time cycle process. We recorded the distance achieved di by each performance. The evaluation function is in the equation 11. You can see in this equation. So t is the number of time step that we define as 1000, and also the alpha t is a torso acceleration for time step t. After optimizing the dynamic gate pattern, we optimize the connection between nociceptor and RG neurons W and S. For this optimization, we found the best motion pattern in the leg malfunction conditions. We use the optimized WRG, WSR, and also WFR from the previous optimizations. We assume that the nociceptor may stimulate its RG neurons with a difference effect. There were 16 parameters, which is WNS11, WNS12 until WNS44. To evaluate each set of parameters, we perform the stimulation for time with different leg injuries. Under normal conditions, the value of Ni was 0. In order to calculate the fitness function, we use the equations 12, where f step is the fitness function of a particular step malfunction performance, and the SAG and the FRO are the error distance of the robot's movement in the sagittal and frontal directions. This optimization forced the robot to move straight ahead with minimal frontal direction movement. This experiment shows the result of optimization processes of dynamic gate patterns and malfunction compensator in a computer simulation using an open dynamic engines ODE. Following this, we demonstrated the dynamic movement of the robots in the context of simulation and real robot implementations. For the robot simulation, we use a cat-like robot with an implemented muscle-based actuator model. We have defined the parameter that not optimized in the table 2. The optimization of dynamic gate pattern process used SSGA, which feature 122 individuals in every population, and we optimize until 200 generations. This figure shows the results indicating the fitness value decreasing gradually. The signal response to the gate pattern was evaluated using different speed simulation. The sample of the robot performance in different speed can be seen in this video. You can see that in the slow speed, the robot tends to move in the walk-type gait, and when we increase the speed, the robot tends to move in the trot-type gait. In this figure, we set esteem parameter from 0 and gradually increase it with the value of the time step. The SPG model can generate dynamic gate pattern from 5 known gate patterns. This range from slow to high speed, walk, amble, pace, symmetrical walk, and also trot gait pattern. However, the symmetrical walk pattern between pace and trot gaits does not exist in the animal locomotion. However, in the proposed model, the symmetrical walk gait makes the transition from the pace to trot gait pattern. After that, we do optimization of malfunction compensation. In this optimization, we use the best parameters from the previous optimizations. There were 64 individuals in each population. We optimize until 200 generations. The fitness function results are shown in this figure. To evaluate the optimized parameters effectiveness, we perform the simulation in normal condition and then disable one of the forelimb or hindlimb through injury. We also gradually change the speed or the parameter of esteem to evaluate the gait pattern response during the leg injury. This figure shows the results, indicating that the proposed CBG model can respond to the leg injury signal through a smooth transition to both forelimb and hindlimb leg injury. There are different gait patterns under leg injuries conditions. The model changed the gait pattern by controlling the signal input using sensory feedback. During the leg injury, the model can still generate dynamic gait pattern by stimulating a different speed. The signal pattern P is changing to respond the absence of CBG signals. The time pace decreases after a leg is injured. Malfunction of the right forelimb is given at the time step is 1380. During injury, the model tends to generate a pattern with the same pace difference at a lower speed. At the high speed, left and right hindlimb feature the same pace. Malfunction of the left hindlimb is at the time step 1400. In this condition, the left and right forelimb feature the same pace at the higher speed. In the real robot implementations, we use similar parameters for the simulation performance. First, we operate the robot with different speed simulation on different terrains. The robot was able to move both flat and natural terrains with a dynamic gait patterns. The robot was able to generate 4 gaits: walk, amble, pace, and trot. The robot also performed the movement transition from slow to high speed by controlling only one parameter, which is parameter esteem. Furthermore, we demonstrated the effectiveness of malfunction compensation by conducting tests in 2 conditions: injured forelimb and also injured hindlimb. In this test, the robot first moved normally. After that, after a few seconds, one of the legs was said to be injured. The robot could generate a gait transition without falling in the both conditions. We operate the robots on both flat and natural terrains. In order to see the detail of the video, you can see in the supplementary video. As the conclusions, this paper has presented an efficient dynamic gait pattern generation based on CBG mechanism with sensorimotor coordination. We use single objective evolutionary algorithm to optimize the networks, a process separated into 2 steps. First, gait pattern optimization, and the second is malfunction compensation. There are 5 patterns generated by robot performance: walk, amble, pace, symmetrical walk, and also trot gait, by using only a single parameter. Force feedback also has a big influence on generating gait patterns. This was demonstrated by the robot performance on the rough terrain. In the real implementations, a cat-like quadruped robot demonstrated the effectiveness of the proposed model on the steep terrain. Actuator control level differed between the real robot and the simulations. However, these were controlled by the same gait pattern and did not impact the effectiveness of the proposed CBG model. As the future work, the proposed model should be applied into more challenging behavior, such as transitioning from ground movement to water movement. For this next step, understanding the role of sensory feedback for the cat or dog water movement will be critical. This is the end of our presentations. Thank you very much for your attention.